Good morning, determinants. So today's slides are not in the book.
What?
The book doesn't go over this. They just tell you how to find a determinant. They don't actually tell you what a determinant is.
In the other book?
Nope. We first have to define a permutation. Given a set of integers 1 to n, arranged in ascending order, one of the very few times where the order of the set matters. So we call this an ordered set. A rearrangement of the elements of S is called a permutation of S. All right, so for example, if you have the set 1, 2, 3, 4, the list 2, 4, 1, 3 would be a permutation of that set. In this case, this has n integers. There would actually be n factorial permutations. And so going back to the 1, 2, 3, 4, there's 4 factorial permutations for the set of 4 integers, and that is 24. So you have 24 total permutations. Say a permutation has an inversion if a larger integer precedes a smaller one. Oh dear. So every time in your permutation you have a larger number coming before a smaller one, it's an inversion. We call a permutation even if the total number of inversions are even, and odd if the total number of inversions is odd. Now we can define the determinant. Consider an n by n matrix A, define it as A sub ij. The determinant function, denoted simply as det, is defined as the determinant of A is equal to the sum plus or minus A sub 1 J1 times A sub 2 J2 times A sub 3 J3, so on and so forth, up through times A sub n Jn, where you're summing over all of the permutations of this set of integers 1 to n. Your sign is positive or negative according to whether the permutation is even or odd, respectively. Nope, I hit the wrong button. So notice that your rows stay constant in your summation, right? It's always row 1, row 2, row 3, row 4 in ascending order. What we're actually finding the permutations of are the columns. And two noteworthy results. First, determinant of A is equal to determinant of A transpose. So taking the transpose of a matrix doesn't change its determinant. And if a row of A consists entirely of zeros, the determinant is automatically 0. Actually, let me change that. It's actually if a row or column consists entirely of zeros, then the determinant of A is going to be 0. Both of these should be fairly simple to prove. Oh, wait. Now someone decided that it doesn't want to show it anymore. There we go. Start with a simple 2 by 2. It's find its determinant. Now, first notice that the set we're working with is just the set 1, 2. First, we're going to find the permutations of this set. How many permutations should we have?
1.
2.
2. How'd you get it?
I just assumed since there's a 2 there, you were supposed to 2.
Remember,
2 in the set.
right, so what does that have to do with it?
It's 1 of each.
Set of n integers has n factorial permutations. 2 factorial is 2. Permutations 1, 2, and 2, 1. Look at that first permutation. How many inversions does it have? None. Second one, how many inversions?
1.
1. Even odd. So then the determinant of A, going to use that first permutation, 1, 2. Right, so remember the rows. So that first index always increases with each term. The second index is the order of the permutation. So that's why it's A11, A22, and it's even, so it's positive. Plus rows go up 1, 2, and the order is 2, 1 for the column. That inversion is odd, or that permutation is odd. So that's negative. So it's going to rewrite it. There's your determinant of a 2 by 2. And notice what that is. How you would evaluate it. A11 times A22 minus A12 times A21. Right, so you draw an X. The direction of multiplication dictates whether it's positive or negative. Right, going to the right positive, going to the left negative. So that is a quick shortcut for doing a 2 by 2 determinant.
Does this work for every 2 by 2? Is this just
Well, that was an arbitrarily chosen 2 by 2, right?
yeah?
So every 2 by 2.
What about like the formula where it's like b over take bc minus d something or dA? B times the matrix. Is that I forgot what the formula was. So there's like a formula to also get you the determinant for a 2 by 2.
Well, that is the formula for 2 by 2
This is the
determinant.
arrow technique, correct? Which is like line.
Well, that's what I just showed how to do, but it's this formula. So if you have ABD or ABCD, right, AD minus BC. Right, one of the questions had that before we looked at determinants. So that's actually what it was. Oops. 3 by 3. Set we're working with now is 1, 2, 3. How many permutations are we going to have? 6 of them. First one's easy, 1, 2, 3. Another permutation. One, 3, 2.
How did you get 6 permutations?
3 factorial. Then you can have 2, 1, 3. Two, 3, 1. 3, 1, 2. And finally 3, 2, 1. First permutation, how many inversions are there?
0.
Second.
1.
Third. Fourth. 2. What about the 5th?
1. 2.
2. And last one has 3. Right, if you look at that 4th one, 2 precedes 3. I'm sorry. 2 precedes 1, which is an inversion, right? 2 is larger than 1. And 3 precedes 1. 3 is larger than 1. 5th one, 3 is larger than 1, so there's an inversion. 3 is larger than 2, there's an inversion. That last one, 3 is larger than 2, there's an inversion. 3 is larger than 1, there's an inversion. 2 is larger than 1, there's an inversion. There's your 3. So even, odd, odd, even, odd. I'm not going to write them out for the sake of space. Determinant of A. Does the order of multiplication matter? Or does the order of addition matter? So when you sum, it doesn't matter the order, right? So why don't we do all of the even inversions first? Keep all the positives up front. And then do all the odds last, because those will all be minuses. That would be the first 3 terms. And those would be the last 3 terms. There's your 3 by 3 determinant. So there is a trick with the 3 by 3 as well, if you look at that formula. Let me do this because I'm too lazy. So you take your 3 by 3. Here's how a lot of books tell you to do it. Take the first 2 columns, I can just stay here, of the matrix. And kind of just attach them at the end. First term, second term, third term, fourth, which is minus, fifth, which is minus, sixth, which is minus. That's not typically how I do it. I've always looked at it this way. If I go back, I'm going to be dating myself. Remember the game Asteroids? They did something that was really ingenious. Right, due to the limitations of computation, they only had so much space to work with. So what they did was they said, okay, well, the edges just loop on itself. That's how I kind of think of this. So I draw my arrow. There's my first term. My second term, oh, but I'm leaving. I'm coming back in through here. There's my second term. I just left the space, but I'm re-entering here. There's my third term. All positive. Then I'll go in the other direction. Negative. I leave, I re-enter the other side. Negative. Leave, re-enter, negative. So I think of that 3 by 3 as sort of the asteroid playing field. And the arrow is the spaceship. Do you think you can do something similar for 4 by 4? Well, you can definitely do the permutations. Unfortunately, how many permutations are there? 24. Screw that. I'm not doing that by hand. I leave that for you. Actually, 4 by 4 is still too easy. Maybe I'll make you do a 5 by 5. How many permutations would a 5 by 5 have?
120.
120 of them. So it's going to be 120 terms in your determinant. There. So there's your challenge. Come up with a formula for a 5 by 5 determinant using the definition.
Is there already a form for that?
Huh?
Is there not already a form for that?
Well, there is. You just have to write it out. There's a method of doing it that I haven't covered yet. As it turns out, the method we just went over with the arrows only goes up to 3 by 3. So the idea of extending your matrix doesn't work for 4 by 4 or higher. That sucks. That's okay. We'll have shortcuts for finding such determinants, which we'll look at next week. We'll look at one such method next week. And then after the exam, we look at the other method. Yeah, you actually should be familiar with one of the methods. Like Calc 3 people definitely are. And anyone who's taken physics should be as well. Cross product of two vectors, 3 by 3 determinant, using a specific method. But for today, we're just going to use the definition. In other words, I'm going to use the shortcut. That shortcut makes these kind of determinants not that terrible. I'll tell you what, use the definition to calculate a 5 by 5 determinant, and you're really going to appreciate the two methods that we go over. So typically when we look at determinants, you can either do like what I did here, write it as det of A. Or if you just have the array already, absolute values around it means determinant of that matrix. Six times 3 minus 5 times 2.
8.
Determinant is 8. Notice what a determinant is doing. You plug a matrix into the function, and you get a scalar out of it. So the determinant is a function of square matrices to the real numbers. Actually, theoretically to complex numbers, but that's if you have complex entries. Oh, that was easy. Okay, what? 2 times 7 minus negative 3 times 4. Oops, not 12. So 14 minus negative 12. 26. And 4 times negative 2 minus negative 5 times negative 1. Negative 8 minus 5. Negative 13. Matrices, we said, had to have real numbers as the entries, right? Think of a real valued function, f of t. Isn't that a real number? So our matrices, the entries can also be real valued functions. By the way, such matrices we'll be seeing a lot later in the semester. Very important later, and very important in the study of differential equations, specifically of systems of linear differential equations. T minus 5 times t plus 2 minus 6 times 3.
Square minus 3t minus 3.
T squared minus 3t minus 28. Back to the easy stuff now, right? So what? Be nice if the exam was what? Just transpose of matrices and 2x2 determinants. Could do those all day, every day. So go 3x3. So first, for this one, maybe I'll do the method introduced by most texts. Of course, I want to be careful. I don't want to use the determinant symbol because that's not actually the matrix I'm finding the determinant of. There's the first three terms of the determinant, right? And you start in the upper left, you move over until you hit the end of the original matrix. And you go to the right. Minus, now start in the upper right corner. We're going diagonally to the left, and we're going to do it for 3 columns. Those would be the next 3 terms. Eight plus 9 plus 40 minus 15 minus 12 minus 16. Eight, 9, 17, 57. 15 and 16 is 31. 43. So 57 minus 43. 14. Yeah? Look, even a 3x3 determinant's not too bad, is it?
So you can't just do like the cross product of two vectors method with instead of IJK, the top row.
Haven't gotten there yet. I will. That's one of the shortcuts. Today is just using the definition. Tuesday we'll go over that. Right, this is kind of, in my opinion, better. This method is kind of easier for 3x3. The other methods are really meant for larger size square matrices, 4x4 and higher. This one I'll call it the asteroid method. I don't know. What do we want to call that one? The shifting method?
Pac-Man.
Pac-Man? Okay, I'll go with that. So 1, 4, -2, plus -2, -1. Uh-oh, I left the space. I just kind of loop around. Three, 2, 5. All right, so it was this. So now I go the other way. And so it was the same concept, except now we're going diagonally to the left instead of to the right. -8 plus 2 plus 30 minus 12 minus 8 minus -5. -8 and 2 is -6. 30 is 24. Minus 12 is 12. Minus 8 is 4. Minus -5 would be 9. So determinant is 9. What would one of the positive terms be in this determinant? So when I say positive, I mean in terms of the inversions. So going from left to right.
Would it be 1 times 8, 1 times 1?
What's a second?
3, 2, 1.
What's the final?
-5, 3, -2.
Now let's start looking at the negatives. What's one of them?
-3, 3, 1.
What's another one?
1, 2, -5, -1.
We all agree? -1 plus 6 plus 30 minus 9 minus -4 minus 5. -1 and 6 is 5. And 30 is 35. Minus 9. 26. Plus 4 is 30. Minus 5. It's 25. Determinant's 25. Do these all day. That's the determinant. Questions on the determinant. And then the obvious answer is, okay, well, that's great for 2 by 2, 3 by 3. What about a 7 by 7? Well, what's 7 factorial?
Too much.
Very large. And actually, it's not very large. It's actually relatively small.
5,040.
Yeah, it's relatively small. That's nothing. What's 10 factorial? That's also still relatively small. That's nothing. That's nothing. If we paid $3 million on a national debt, it wouldn't even notice. It would be like a spaceship flying into the sun. Someone would just burp, and that'd be it. So again, that's still relatively small. But again, do you want to do, 10 factorial permutations by hand? You'll be at it for a while. If I gave it to the end of the semester, you could probably do it, but how much sleep would you get? I could do that. Just start Tuesday off with a test, single 10 by 10 determinant using the definitions, give you the entire semester to do it.
That's torture.
Be like your only grade for the semester.
That's the.
And I have to show every single step in every term. Well, that's where two methods come in handy. First is cofactor expansion. Cofactor expansion is great for 4x4s. A little bit more tedious when you're dealing with anything larger than that. Still doable. It's a bit more tedious. The other method is row reduction. And by that, I just simply mean using row operations. Get into a triangular form, and then the determinant is really easy at that point. That method is very nice, especially for larger matrices. Fortunately, we don't look at that method until after the exam, which is a shame. So today was an easy day. So second discussion assignment, don't forget your initial posts are due tonight. Responses will then be due Monday night. You have two.
Session says that it's on June 17th. And
Why is... Yeah, what's going on here? Oh dear. What the hell was I drinking at the time? So why are there two homework 6s? I would assume that's a typo. Oh, I haven't fixed the link on here yet. Oh dear. Oh, there it is. So let me find out what's going on there. So I also have a couple of announcements, so don't leave yet. Yeah, so that, okay, why is there two homework 6s? I don't know. Homework 6. There is no homework on what we did today because the book doesn't use the definition. So you get a day off of homework. The second project is available. Groups have been assigned. I believe the second project went up this morning or just before class. So that will be due the end of February, the 27th. Don't forget, the first exam is next week, next Thursday. Covers everything up through and including what we do on Tuesday. Speaking of Tuesday, there may not be class. I have an appointment in the morning. I'm not sure if I'll get done in time to make it here. But I will make it in time for my afternoon session, the one that's right after this. So that recording will go up if I have to miss this class. This class is larger than I thought. I was going to invite you to the afternoon session, but I don't know if there'll be enough seats. If you want to come, we can make it work. So I'd rather just show up for my 1:30 session instead if this class gets canceled. Just get here early because you may have to stand if you're late. But that's entirely up to you. I will record that session, post it if I have to cancel. Keep your eyes peeled on Teams. If I have to cancel, if the appointment runs long, I'll let you know. Otherwise, have a good weekend.